Welcome to this first in a series of videos intended for students in college-level mathematics, typically at the sophomore and junior level. My target audience consists of students in foundational courses in algebra and analysis, many of whom are just trying to get up to speed with reading and writing proofs. I find that talking about proofs scares a lot of students, so there's a lot of elephants in the room when it comes to mathematical abstraction. In this first video, I would like to face one of the many elephants in the room, the concept of a number. And so I ask, what is a number, generally? Or what is a real number? Or a rational number? Or what is meant by a particular number, such as the number we call 2, or the number square root of 2, or pi, or I? You've probably been surrounded by numbers for most of your life, and some of the questions I'm asking you would have taken for granted. But I do find that most students at the level I'm speaking to cannot really say what they mean by a number. And there are a lot of prevailing misconceptions about what numbers are. So let's hash them out, maybe clear the air a little. The word number, however, is a surprisingly subtle word which has no single universal meaning. Actually, there are many different kinds of number systems, and each number system typically has elements we call numbers. It's much easier to define a number system than to define a number. And even number system is really too vague, but many of our most important or well-known number systems can be defined precisely enough with work. Many of these number systems are structures we call rings and fields, and these are terms that have very specific meanings in mathematics. In very loose terms, a ring is a number system like the integers where the operations of addition, subtraction, and multiplication are defined. For example, if you add two integers, you get an integer. Similarly for subtraction or multiplication. Each of these operations has two inputs, so it's called a binary operation. And the output is, again, an integer. In order to qualify as a ring, the operations have to satisfy certain properties, such as 5 plus 3 equals 3 plus 5. A field requires a little bit more. Here we have not only addition, subtraction, and multiplication, but also division, where we require that an element of a field can be divided by any non-zero element of the field, giving an answer which is in the field. So the integers do not form a field, but the rational numbers do, and so do the real numbers. Here is a list of what I would call the big 5 number systems that every student of mathematics comes to know. They form a hierarchy. Each one is contained in the next. Despite their ubiquity, they are hugely misunderstood by students. I find that students have a very basic misunderstanding about a lot of what goes on in these number systems. Let's start with the natural numbers. On a technical note, some textbooks list 0 as a natural number, others don't. I'm going to omit 0 from the natural numbers, since one of my textbooks this semester does that. We'll just say the natural numbers are the positive integers. This is a number system with addition and multiplication as its most basic operations. These operations satisfy various commutative, associative, and distributive laws, but subtraction is not a binary operation in this system. For example, 3 minus 7 is not defined in the natural numbers. So this can't be a ring, but this is a bona fide number system, and it's very important because we use natural numbers all the time for counting purposes. Extending the natural numbers to include all integers, positive, negative, and 0, we obtain our first example of a ring, at least the first example most people encounter. Next up is the set of rational numbers. Unlike the previous examples in our list, this number system is a field. Here, we are able to not only add, subtract, and multiply elements, we can also divide, as long as you don't try to divide by 0. Next up is the field of real numbers. For those in my real analysis class, this is the most important thing to come to understand. It is probably one of the most widely misunderstood structures in all of mathematics. Finally, we have the field of complex numbers. My students today have a much better understanding of complex numbers than students of 20 or 30 years ago. Yes, I've been teaching college math that long. I will devote one of the later videos in this series to properties of complex numbers, which I believe are essential for a proper, complete understanding of the real number system. Now, there's quite a lot going on here, which I believe most students take for granted. So before we push ahead, let's comment on some of the finer points here, starting with the natural numbers. Let me warn you, humans do not fully understand the natural numbers. There are many unsolved problems in the theory of natural numbers. This is the goal that motivated number theory. So there's a lot of meat to chew on here. And yet, if I ask my students to define the number 2, I find that most of them will have trouble. I also expect most students will have an easier time thinking of 2 apples or 2 books. The concept of 2 as a number by itself being a more abstract notion. I'm not claiming that this statement is adequate as a definition of the number 2, but I'll suggest that any attempt to define the number 2 must grapple with the fact that 2 is an abstract concept. What do I mean by abstract? We have courses in abstract algebra, other abstract mathematics, including analysis, but the word abstract here does not refer to esoteric or hard to understand. What abstract does mean is simply general. By talking about the number 2 rather than 2 apples or 2 books, we have abstracted an idea motivated by some understanding of the physical world, the physical reality that surrounds us. The idea of 2 then becomes generally applicable in a variety of contexts beyond whatever could have been anticipated by the first person to invent the concept of 2. Whenever we talk about abstract algebra or abstract mathematics, our goal is this: not to be esoteric, but rather to describe patterns and principles that apply in the greatest possible generality. So what does 2 mean as an independent concept? By the way, the natural number 2, is that the same as the real number 2, or the complex number 2? When we talk about 2 pounds of butter, isn't this something more subtle than 2 books? I guess if we have 2 books, we have exactly 2 books most of the time. But if you have 2 pounds of butter, does that mean exactly 2 pounds of butter? All the big 5 number systems have an element called 2, but when we talk about 2 in each context, are we being too quick to think about 2 as the same thing in each case? These questions are not really just for philosophers, they should be for mathematicians. Actually, the questions of trying to stitch together our different mathematical structures, including number systems, to take account for what we consider sameness in mathematics, is a widespread problem, and particularly it comes up all the time in modern efforts to make computers do the formal thinking for us. So does the number 2 exist as a concept independent of 2 apples or 2 books or 2 pounds of butter? Is there possibly more than one meaning of 2, depending on the context? There was a time in history when you could have been ostracized, or maybe even killed, for declaring the existence of square root of 2 as a number, or the existence of 0, or negative numbers, or I, or certain transfinite numbers, to name a few examples. Questions like the one at the bottom of our screen here are not strictly mathematical in nature. They are maybe philosophical, but I would argue that existence is more of a semantic problem. Ultimately, all numbers, great and small, all numbers in these big five number systems are pure abstractions. Numbers like square root of 2 and I exist in the same way that 2 does, no more and no less. We have more substantive questions to consider, like, do these ideas make sense? What do they mean? And of course, how do we use them to solve problems? Now, let's push forward a little. What I call the big five number systems are not the only number systems we have, certainly not the only ones we care about or the ones that we use. First, I want to dispel the naive idea that all numbers lie in some kind of a hierarchy extending the big five, lying in a simple sequence, with each one contained in the next. Here is just a very small sample of the veritable zoo of the number systems that exist. There's really no limit to the number systems that have been conceived and studied. All these number systems shown here have the same claim to existence as the big five. Many, but not all of these number systems are fields. All have application to important problems in what we call the real world. All of them are essential to a complete understanding of the real numbers and even the natural numbers. A few words about terminology, at least for the big five. We can hardly argue with the name natural numbers for the positive integers. At least most people, whatever their personal philosophy, will accept these numbers are in some sense found in nature. The font that is used here with the double strokes is known as the Blackboard Bold font. It is distinguished from other fonts used inside and outside mathematics. These double strokes form the Blackboard Bold font. Integral means whole, so integer means a whole number, a number without any fractional part. The capital Z comes from the German word Zahlen. The rational numbers are precisely the ratios of integers, so this name makes good sense. And Q stands for quotient, which is synonymous with ratio. Let's skip over the reals for a moment and mention the terminology of complex numbers, represented by the letter C. The word complex is often confused with complicated, which is quite different word. In fact, the complex number system is much simpler than the real number system in many ways, as students of both algebra and analysis should quickly discover. I will argue to defend that point in a future video. For now, let me explain that a complex is simply a structure made up of separate parts. Just as a sports complex may be composed of an arena, a stadium, a track, and a gymnasium. The vitamin B complex is made up of separate B vitamins like B1, B2, B3, B5, B6, B7, B9, B12. I think there are 8 of them. Last time I checked, maybe there are more by now. The name complex number refers to the fact that you can think of it as having 2 parts, the real part and the imaginary part. That's the A and the B in the A plus BI. So when you refer to a number as complex, you're saying it is composite. It is made up of 2 parts. Finally, the word real, in reference to real number, is a word chosen for historical reasons. The Blackboard Bold R here, of course. Of the 5 names for the big 5 number systems, this name is the least appropriate and the most misleading. For one thing, all numbers have some connection to reality. The complex numbers are essential to an understanding of our physical universe. The real number system is very useful in modeling some descriptions of physical reality. They're not the right ones for counting, but for measurement of physical quantities like time, distance, mass, temperature, etc. But real numbers are not the same thing as physical reality. They're not the reality of physical quantities. The basic principles governing physical quantities and measurements are more mysterious than most people realize. Also, the basic properties of so-called real numbers are more mysterious than most people realize. And the weirdness of physical quantities is different from the weirdness of the mathematical number system of so-called real numbers. And I know people who would reject what I'm saying here, so feel free to disagree. But I believe people who don't recognize these facts I'm saying just simply have not seen enough. You may consider it a philosophical issue irrelevant to a study of real numbers. But I maintain that if you're getting a college degree in mathematics, you should have some awareness of what its connection is to reality. More awareness than perhaps we often find in our curriculum. More on this later, so we'll get back to that. For now, let's get back to the big five with a fresh awareness and a humble realization that while this may be an important part of mathematics, it is still really a small part of the big picture. I emphasize that 3 of these number systems are fields, where we can add, subtract, multiply, and divide. 4 of them, including the integers, are rings. The natural numbers are not a ring because they do not permit subtraction as a binary operation. I mention the very complicated zoo of number systems, of which our big 5 are just a very small part. 2 important number systems that extend the complex numbers are the quaternions, denoted by H, and the octonions, denoted by O. These number systems are very important in both mathematics and in physics. These are not fields in the strict sense. They are not commutative. In fact, the octonions are not even associative. They have applications closer to home. For example, ask me sometime about the role of quaternions in computer graphics. If we extend the integers by throwing in square root of 2, we get a ring, z of square root of 2, and this ring extends to a field, q of square root of 2, generated by the rational numbers and square root of 2. These numbers are very important in number theory. There are many examples of finite fields. These are fields with a finite number of elements. F3 is popularly known as the integers mod 3. These are extremely important in information theory, in particular in modern cryptography and the theory of error-correcting codes. I mention them partly to underscore that real-life applications of mathematics are not limited to the big 5 number systems above. I happen to be a mathematician who uses finite fields on a daily basis, although I suspect that most mathematical literature in the subject of finite fields is to be found not in true mathematical journals, but rather in electrical engineering literature. Here are some other examples of fields and rings which extend the complex numbers in a more obvious way than we do in the quaternions and octonions. These consist of polynomials and power series. You might suggest that we're no longer talking about numbers here, that somehow these rings and fields are some kind of functions rather than simply numbers. But I need to assure you that I'm including them here for a reason. They do have a formal life that is much more similar to real numbers than to the functions you're used to. Formal polynomials and power series are at heart actually numbers, not truly functions. I'll talk about these issues also in a later video. This fancy R with the hat on top is the symbol that I will use for the hyperreals, or the non-standard reals. This is an extension of the real number system where we include infinite and infinitesimal values. At first glance, this structure looks a lot like the real number system. Polynomials still satisfy the intermediate value theorem. It can be used as a foundation for calculus, as an alternative to the epsilon delta formulation, which has become the standard approach of our undergraduate curriculum. Arguably, it provides as realistic a description of physical lines as the traditional description using the real numbers, in fact with some advantages. Here, Z3 and Q3 are a ring and a field, respectively. extending the usual integers and rationals. The prime 3 here happens to be an example which could have been replaced by any prime number. Q3 is another kind of alter ego of the real numbers. These are known as the three-adic integers and the three-adic numbers. They are not to be confused with mod 3 arithmetic. Just be warned, since it is popular in many undergraduate textbooks to use Z3 for the integers mod 3. These number systems are important for a complete understanding of the other number systems on this slide, especially the rationals. Understanding the rationals is more subtle than you might imagine, and in many situations, an understanding of the rationals depends on an awareness of how the rationals are simultaneously embedded in the reals and in all the p-adic extensions. I have spoken very loosely of what we mean by a ring, but once and for all, let's make the definition precise. You can easily look this up later if you need it. I'll take a set R, ordinary R, not blackboard bold R. We'll take a set R with a special element I'll call 0. We want to have three binary operations called addition, subtraction, and multiplication. I'll write minus a as a shorthand for 0 minus a. This, by the way, is now an example of a unary operation, since I'm mapping a single input a to a single output minus a, although the unary operation is easily specified as coming from the binary operation of subtraction. Here is a list of the commutative, associative, and distributive laws that we require to universally hold in order for R to be called a ring. In other words, these are the axioms of ring theory. Note that multiplication is not required to be commutative. Also, in general, we do not require an identity for multiplication. But when studying ring theory, please pay attention to each author's conventions, because some authors' books specify up front that their rings have to be commutative or to have an identity. Again, I have loosely described a field as a ring in which division is allowed. But here we need to be precise. So this is the definition of a field. We start with a set F, having at least two distinct elements, 0 and 1. So note that a field always has at least two elements, which is different from in a ring where you might just have a single element, 0. We require four operations: addition, subtraction, multiplication, and division, defined for all pairs of elements, except that you do not allow division by 0. As before, we introduce a unary operation, mapping a to minus a. This is, however, shorthand for 0 minus a. And we require the following list of properties to hold universally. This list extends the list of properties from the slide about rings. Note in particular that we now require 1 to be a two-sided identity for multiplication. Also, multiplication is required to be commutative for fields in the strict sense. Now, in the older literature, this was not required. Nowadays, we do require commutativity to distinguish skew fields where commutativity is not required. So, fields require commutativity nowadays. A little more about basic properties of our big five number systems. The integers form what we call an ordered ring. This means every integer is either positive, negative, or 0. And this gives a partition of the integers into three types with no overlap. We'll talk more about partitions in a later video. The negatives are obtained from the positives by applying our unary operator of negation. This partition satisfies some essential properties. If we add or multiply two positives, we get a positive. Also, positive times negative is negative, and negative times negative is positive. This partition gives us a way to totally order the integers. We say that a is less than b if b minus a is positive. A is greater than b if b minus a is negative. So the law of trichotomy holds. If a and b are integers, either a is less than b, or a is equal to b, or a is greater than b. One and only one of these three relations can hold for a given pair of integers a and b. This ordering of the integers plays well with our algebraic operations, and the usual manipulations hold. For example, if we start with a is less than b, then we can add any integer to both sides. The inequality is then preserved. If we multiply c on both sides, we also preserve the inequality, at least if c is positive. If we multiply both sides by a negative, we reverse the inequality. All these familiar properties follow from our assumptions about the partition of z into positives and negatives. Similarly, R is an ordered field. The ordering of the real numbers is again defined by starting with a partition of the reals into three types: positive, negative, and zero. And as before, inequalities work like you should have learned in high school. The first and most important distinction between the real numbers and the complex numbers is that the complex numbers do not form an ordered field. Let's prove this. Our proof will be by contradiction. So suppose that the complex numbers somehow form an ordered field. Since I is not 0, it would have to be either positive or negative. Now, what is minus 1? Is that positive or negative? Well, minus 1 is I times I, which is either positive times positive or negative times negative. Either way, according to our rules, that would mean minus 1 would have to be positive. Actually, we don't have a contradiction yet. But now what about 1? Well, 1 is minus 1 times minus 1. Positive times positive makes positive. So 1 is positive. Now, 1 plus minus 1 is 0. We're adding two positives, so we'd have to get a positive. That violates our rules. We required 0 to be neither positive nor negative. This is a contradiction. So, the complex numbers cannot be an ordered field. There's no way to define an ordering on the complex numbers to make it an ordered field, according to the definition. The other important feature which distinguishes the complex numbers from the real numbers is that the field of complex numbers is algebraically closed, whereas the field of real numbers is not. Here's what we mean by this. Take any polynomial f of x of degree n greater than or equal to 1 with complex coefficients. Then f of x can be factored as a product of n linear factors. This is the same as saying that f of x has n complex roots, n roots in the complex numbers, although the roots do not have to be distinct. By contrast, the real and rational numbers are not algebraically closed. Here's an easy example of a polynomial of degree 2 that cannot be factored into linear factors, factors of degree 1, over either the reals or the rationals. So this polynomial, x squared plus 1, is irreducible, both in q of x and in r of x. Here is a polynomial of degree 4. It's irreducible over the rationals, but it's not irreducible over the reals. You can factor it as a product of two polynomials of degree 2. These examples are somewhat typical of what happens in the reals and the rationals. In every polynomial in x with real coefficients, you can factor into irreducible factors of degree 1 or 2. That is, linear and quadratic factors. is a very important fact we use in calculus as a stepping stone to finding antiderivatives for rational functions. Second semester calculus does this. But I should mention that this fact about real numbers would be very hard to prove without knowing that the complex numbers are algebraically closed. And this is just one instance of how the complex numbers simplify our work when trying to work with the real numbers. Over the rational numbers, there are irreducible polynomials of every degree. And once again, an indicator that the rationals are in many ways more complicated than we tend to realize. I'll leave you with a homework exercise. Show that one of the examples I mentioned earlier is an ordered field. This q of square root of 2, q bracket square root of 2 is the set of all numbers of the form a plus b root 2, where a and b are rational coefficients. So show that this is an ordered field. A big part of the proof will necessarily involve showing that this is closed under the basic operations, including division by any non-zero element in the set. Showing that it's ordered should be easy. But how about this? Actually showing that it has two different orderings. There are two different ways to define your partition of this field into positive, negative, zero elements, satisfying the algebraic requirements. Consequently, there are two different ways to make this an ordered ring. I'm pointing this out that the ordering is not required to be the, quote, usual one. You should have no preconceptions about what the ordering is. Unless you understand this, there's a good chance you missed the point in the earlier proof about the complex numbers not being an ordered field. Halfway through that earlier proof, we reached a step where -1 is positive, but I didn't yet have a contradiction. The point there is that we cannot have any preconceptions about what the ordering is. All we have here are the axioms for an ordered field, as laid out earlier.